said what Malloy takes as input, what does it take as input? Do you guys remember? In the front? Does it take a void pointer as input? I don't think that's the input. Like, so, like, if you gave it a pointer, like, then you already have, like, a section of memory you want to, like, store something on. Because the pointer is really an address. And so you'd be giving it an address saying right to this location. But the thing is, you don't determine where the addresses are. The computer does. Void pointer is something that's important, and we will talk about in a moment. But that's unfortunately not quite the input. What is the input then? I see someone in the back, but I've already called them. Yeah, over here. Yeah, it's the size in bytes. The desired block size in bytes. All right. So what does malloc give as output? I want to call in someone new if possible. I want to call in someone new and not a TA if possible. Yeah. Void? Is it void? It's close to void. Void star. What does the star mean? Not quite sure. Okay. So yeah, so the star means it's a pointer. So whenever you see like int star, what does that mean you have? Like if you have a function where you say int star x, what is x really doing in that situation? It's an address. It's an address of something. An address really means that it's a pointer. The idea is like if you know about the memory structure, this is hopefully something you talked about in your, actually you might not have talked about it, interesting. I mean, at least not from the dynamic memory point of view, but like hopefully you talked about it when we went over pointers. The idea is that you'll have some like memory structure, and then assuming that we're using the stack, we are basically using everything that's like up here. So like we have our main function, and the idea is like we can have some like x here, and like if I said, you know, int star x, what value will x belong to? Like what's going to be the thing in this section of memory that's associated with it? It's going to be what? Is it going to be empty? It should have values in it, hopefully, at some point. It might be empty when, hopefully it's like 0 when you start it off, or like you initialize it and all zeros, and I'll talk about why that's the case maybe in a moment. If this is supposed to be a star, this really should be some address. And the idea is like, so like, let's say this is address 1. So my question is, would this be address 1 here? Is like, if I were to go ahead and say the addresses, would you think x has address 1? The answer is no. And the thing is, you could argue, well, could we not store address, like, you know, x's address into x? And the answer is yes. But then the issue is now you're not working with an int star, you're working with an abomination. Because the thing is, this is not pointing to an integer now, this is like pointing to an int pointer. So really, it would be an int star star. But the thing is, if x was an int star star, then that means it would really have to be an int star star star. Which means that it has to be an int star 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 star. And then you see how that can maybe get a little bit complicated. It's recursive, if you know what recursive means. We'll learn in a bit. But anyways, the idea though is that x would point, like if I said something like int y, and I wanted to relate x and y, how could I relate the two? Like how would we do this? This is hopefully something you did in your intro to C class. So yeah. We want to use the ampersand somehow. So how would I go ahead and have these guys related using the ampersand? Like I want to do some initialization here. So I think you agree that I could say like y is equal to 1. Is that valid? Could I do something like x is equal to 1? Does that make sense from the computer point of view? No, I see a lot of people shaking their heads. Very good. So this is not what I want to do. What would I say x is equal to then? So it's ampersand y, not just y, it's ampersand y, because the thing is, y is somewhere here in memory, and it stores some number. In this case, I guess it stores 1. And assuming that we're saying x is equal to ampersand y, that means where y is at, it has to be address 1. So that means like this is like kind of the behavior that we're going to get in our function. What is x's address? X is address 2, I don't care about it. I just know it's not address 1. And so this is kind of like what's going on in your memory. And so the idea is like this guy here really points to this section of memory, and that's why we call these pointers. It's like go to this location in memory, use whatever is in that location as the value. So if you want to get the value of what x points to, what do? Do you guys know? We use the star. So the thing is, if I just say, what is x? X is going to say address 1. But that's not really useful. So what we end up doing instead, if we want to get the value that's stored in y, and again, this is something you should have learned in your Intro to C class, you want to get the value that x points to, you want to go ahead and do star x. And the idea is that's going to get the value out. Why does that get the value out? That's something that a lot of people have questioned. Well, think of it this way. If x is a pointer, like an int pointer, because this is what we have going on here, star x is really kind of like an integer, because the idea is like if you int star x. So the idea is like if you have an integer that is like pointer x, so like if you do x pointer, the idea is that this is going to be some integer. So doing this here will get the integer out. So this gets an int. So like this is like maybe a silly mnemonic to remember, but the idea is like if you have int star x, the idea is star x is an integer, and so to get the value of an integer out, you use star x. And this is, again, hopefully something you learned in your Intro to C class. All right. So what does Malloy give as output? It gives a void pointer, which is void star, and hopefully now that makes a little bit of sense. The idea is that if it gives you like void star some thing, the idea is that you're really, if you do star that value, you end up getting void, which is weird. We don't like that. So what do we, I don't know if I talked about this in class, but technically it's 302, so class has officially begun. How do I turn that into the proper type? Like if I'm trying to make an int star, how would I want to make an int star? But like hypothetically, if I wanted to make an int star, does anyone know what I have to do to turn the void star into an int star? Cast it, yeah. So we're going to cast it, and casting, you can kind of think, it's not really related to fishing, although that does sound like a nice thing. I believe it's supposed to be related more to like metallurgy, and when you're like trying to make something, like if you're trying to make like a shoe or something like that, why would you make a metal shoe? Don't ask me. But like the idea is you'd have like a shoe mold and like really a cast, and you go ahead and pour the fluid into there, and it basically takes that form. And so that's what you're doing here, is you're like turning one piece of memory into another piece of memory by doing a cast. Does anyone know how to do casting in C? No? Okay, good. Oh, there's a hand up in the back. Yeah? Yeah, at the front, right? Yeah. All right. So we'll do that. But I just wanted to go ahead and get that out of the way. So the thing is, this doesn't return like an int star. This really returns like a void star, which means it's a pointer to really anything, and you need to do a casting to fix that. All right. So the last thing I wanted to do as a recap is write a snippet of code that dynamically creates an array of 100 integers. I did it at the end of class, an array that created 10 integers. So this is going to be more, but it's really not going to be much different in terms of code. So how do I create an array dynamically? An array of integers dynamically. So I need to do a cast. All right. First of all, let's go ahead and actually assign this memory to something. So what I'm going to do is I'm going to do int star array. All right, so I said I would get to this. Why am I saying int star here? Why is this an array? Why is this int star considered really an integer array? You guys remember? So if this is a star, what does that mean as array? What is array? A pointer, right? And what do we know about the relationship between pointers and integers? Or, sorry, pointers and arrays. Sorry. Yeah, like arrays are pointers. You wouldn't really... I don't know of anyone that says all pointers are array. I mean, I guess they're kind of correct, but like the worst kind. Like how does a void array work? That makes me uncomfortable. But like, so if you have an array, it's really a pointer. And so what we're going to do is we're going to make an array by making a pointer, and that's going to go ahead and fulfill what we need to do here. All right. So now, what's the next thing I need to do? I'll help you guys out. Equals what? Okay, Malloy. Do I do any parentheses anywhere? Around the Malloy?
No.
Oh, okay. Size of, and the size of is all one word, and then you do int in parentheses, and then what?
Multiplied by how many ever?
How many we want, very good. So multiplied by how much? 100. And so the idea is like, if you wanted to make 100 integers, really you want to make like some integer size plus some integer size, plus some integer size. And if you want to make 100 of these, you want to basically add up 100 integers together, and that's how much memory you need. But like adding up 100 times the size of it is like silly. Why would you write that code? Instead, just do a multiplication. There's an answer to that.
Why wouldn't we do 101 or 102?
Okay, so you could do that if you wanted to. That's really important when we're using strings which have null terminators, or if they have the null terminators in new lines. But we don't really have the concept of a null terminator with integer arrays. The idea is like, there's not really, as far as I'm aware, a int array function library that's like built into C. So the idea is you would make all your own functions that would modify the ints, so you can kind of declare them however you want. So if you want to make them like terminated by some sentinel value, like if you want to terminate them by null, I guess you can do that. But that's not really a requirement. So if you want, if I was expecting to have a sentinel value, then yes, I would need a 101 here. But because I didn't clarify that I was going to be making a sentinel, I don't actually need to do 101. But it will depend on your program's implementation. I personally recommend not using a sentinel value, because if you use a sentinel value, that's like one less value you can use an integer. Right? I know that like seems very petty, but that's just my opinion. Additionally, I hate accidentally, if I make like infinity like a sentinel, I hate accidentally modifying it and then having some really bad stuff happen. It just requires a lot of extra checking, in my opinion. I mean, you still have to do checking the way that we're going to be doing this, but I think it's easier. All right, so there's one thing I missed that I think is important, and I left space for it. What did I miss? The cast. So we need to typecast. All right, so do we need to typecast? The answer is no, but you should. It's something that's required in C++. It's just like a safer thing to do than to like just trust that something will be automatically turned into something else. It's a good habit to get into. Good habit start early or something like that. I don't know what they're actually saying, but like it's a good thing to go ahead and do in general, especially because if you do plan on using this in C++, like one, you have some issues, and then two, you're going to need to do this casting, otherwise you're going to have problems.
Is the cast with the parentheses or?
I normally do parentheses here, yeah. So you do include parentheses when you cast. All right. So this is a integer array allocation. Yay! Ta-da! We basically have now hit the beginning, the end of last class, and we're only 7 minutes in, so good timing so far, Travis. Let's talk about the other dynamic memory functions. We'll talk about why we never use them. That's a joke. We should use free, and realloc is okay. Calloc is just kind of pointless. So let's talk about calloc first, because it's like largely not useful. I don't know if you feel that way, Jim.
I find it, okay, history lesson.
Sure.
It used to be useful.
Because you could get failures from malloc without it actually telling you that it failed?
No, because the result of the multiplication of the sizes for calloc could be larger than the
Overflow? Okay.
for malloc. That's true. But the fact that it zeroes everything is not a separate mem copy for mem set. It can't be.
Yeah, so I've heard some people argue that the mem set takes time, and that's why they don't like calloc, but that's not true, because it's really easy to flag things to zero, like nowadays, right? Because you just like say the page is 0 or something like that.
The thing is, I mean, if you're using calloc for that reason, you would just use malloc if you didn't do that.
Okay.
You could also argue that's harder to read.
This is harder to read?
No, it's
Oh,
harder
calloc.
because
Yeah, so some people mess up calloc. All right, let's actually talk about calloc. Let's not get too much into the details. Let's go ahead and talk about calloc first. All right. So calloc is very similar to malloc. The things that it's similar is it actually has the same error and it has the same return value. So what calloc does is it returns a void pointer. Yes, it's dynamic. You should free it. So this is like why it's similar. Let's see, anything else that's like very useful to say in terms of its similarity? Not really. Like dynamic memory functions are pretty easy. It's just like knowing when to use them and like how to use them is like maybe the tricky part. All right, so how it differs. So this is the same for malloc. Significantly how it differs is the argument count and type. So difference. One is the arguments. So what it does is it takes in the number of items, and then it takes in as a second argument the number of bytes per item. So bytes per item. So before, what we had to do is we had to multiply these two guys together. And when you multiply them together, like what you end up getting is like unit cancellation. What you end up getting left over is like the number of bytes. But for calc, what it does is it takes them in as separate arguments. And then, yeah, in older systems where like you could very easily need to create more memory than I guess the size of size t, then like you end up like causing some issues here. But that's not really an issue nowadays. So calc is like safer. And then, or sorry, now looking calc are about safe. And the second thing is the initialization. So what happens is calc fills everything with what? Does anyone know? Zeros. That's pretty much the answer. What I really want you guys to know is the 0 byte. So the idea is whatever the 0 byte is, that's what ends up filling your array. And for basically any normal data structure or data type that you'll be using, the 0 byte value will be 0. So if you want to think of it as being filled with zeros, you can do so. But really, it's filled with 0 bytes. Not 0 bytes like there's 0 bytes in there, but like the 0 byte is what, like, never mind. All right, does it hand us all that? Yeah?
Can you zoom in a little bit?
Can I zoom in a little bit? Yeah. Maybe that's too much. Is that good? Can you read that?
Yeah.
All right. Is there another hand? I thought I saw another hand at some point. All right. So I guess we'll continue. So this is like really nice to be aware of. It's really not that hard to go ahead and do so. So I'm just going to show you a calc method creating an array of size 100. So another example, 100 int array. We do int star array is equal to cast it because it's going to give you a void pointer, so we make it an int. We do calc. We do the number of items, so we're doing 100, and then we do size of int. All right, that's it. Pretty easy. Any questions? Yeah, of course. Just to compare the difference. So in this one, we had to multiply them together because it's taking only one argument in. This one, we're taking the two arguments, and so that's why we have to use commas and I guess two different arguments. Yeah.
So why don't we use brackets with that?
Why don't we use where brackets here? So the thing is, like, we're not. So when you use brackets, like the square brace things, like the square brackets, what you're doing is you're kind of either doing a dereference, or you're kind of saying this is going to be a static size amount of memory, and like we're going to create multiple of this memory in that one allocation. So the idea is when you do something like int array, so this is like static. So when you do int array bracket 100, like this is saying that we're going to create 100 copies of these, but all in the stack memory. It's not like actually going to be going somewhere special. So the thing is, like, this is like the difference. Is like to get access to dynamic memory, you can't like just go ahead and do bracket and get dynamic memory. So what you have to do is you're using this function call, and that function call is going to grab some piece of memory for you and give it to you. And so the thing is, like, you have to basically leverage this other function that exists in another library. Which library is this in? Do you guys remember? Yeah. So all these functions, so the dynamic memory functions, are in standard lib. Lowercase s, by the way. I'm just not going to write it. But, so what that means, though, is that these are functions. These aren't like just things that exist, like, you know, primitively in your design. It's not like a native thing. You have to include this library, and the idea is then you have to use these functions. So you have to do a function call to get the values. So we're not creating an array. We're like really calling a function. That's like the difference. And so that's why we're not using the square brackets, just because we're using a function call to get the memory. Does that clarify a little bit? All right, cool. Yeah, that's I guess the difference is like you're using whatever dynamic memory stuff to go ahead and generate this. We're not like creating stuff on the stack. All right, yeah, another question.
So just want to make sure. What we did with calc, we have 100 arrays.
We have 100 integers, not 100 arrays.
Oh no.
100 arrays is a little bit intense. We can do that though. But yeah, so we have 100 integers, and each integer is going to be sized in. So really this says we have 100 items, and each item is going to be the size of an integer. But we're casting this to int array, so that means that it's gonna make it into effectively an int array for us.
So, we basically did the same thing as,
This is like the same line as this with some mild exception, which is that the memory is not initialized for us up here. So there's no initialization. But this is all filled with byte by zero. And the byte by zero integer is 0. So effectively, every integer in this array will be guaranteed 0. Yeah, there's an end in the front?
Yeah, for the silo, it's actually, it's not guaranteed that every single integer is like specific, like you could have like 5 or 500.
Yeah, so they actually use the exact same amount of memory. So if you have 5, 5 actually is still stored with 4 bytes in my computer, which means that we have the byte that represents 5, typically in the least significant area, and then where we have a 0 byte, 0 byte, 0 byte. So the number 5 actually does store the same amount of memory, or is stored using the same amount of memory as like 500, and it uses the same amount of memory for even like a billion. So billion is just like a lot of bytes in it, like every byte's being utilized, but for 5, it still uses the same number of bytes, but it just like fills the bytes that are like unuseful with 0. So even 0, like you could argue, well 0 takes no memory because there's like no values in it, but 0 still takes up 32 bits in my computer or 4 bytes because each spot is filled with a 0 byte.
So the size of is that like a known byte size then?
It's known for every computer, but the thing is, like you have to be in that computer to get that information. So the thing is, in my computer, integer size of int is 4, but older computers it's like 2. It depends on like, so there's like a standard that says like these are the ranges that you can have. So like the int will always be in the range of like I think 2 to 4. I don't think is there systems that use 8-bit like integers?
Some 64-bit systems actually use 8-bit integer as well as 8-bit pointers.
Really? So they use like if I do int, it creates like 4 bytes. It doesn't create like or sorry, it creates 8 bytes instead of 4 bytes.
Yeah.
That's weird.
I can't remember where I saw that, but there's at least one system out there that does it.
Okay, so yikes. All right, so I guess with the more modern computers, those upper bounds are going to be increased. Do they have, like, what are the long ints then in that system? Is it still 8?
I think they're
You know what? Don't worry about it. We'll find out if there's anything really crazy. But the thing is, if you don't want to go ahead and hard code this saying, like, let's just make the biggest thing we need. Like, let's go ahead and say if they're 8 in like the biggest system, let's just go ahead and make them 8. Because that means if you're doing like an embedded system that's like you have to like have a limited amount of memory, you're gonna have to like maybe deploy this, like maybe it's gonna be like in a sneaker or in a coffee maker or something like that. You don't want to have to make a whole lot of memory. And additionally, like the bigger like these sizes are, if you were putting something like really heavy duty in there, that's gonna be more expensive. It's gonna take more resources. It's gonna be like just kind of more problematic. So you want to like ideally use as little stuff as possible because you know if you allocate this memory, that is less memory that those systems are going to be giving overall.
So like calling size up int will give you whatever byte size int is.
For whatever system that you're compiling on, exactly. Yeah. Perfect. So size of int will always give you what you need. This function is built in to the thing. You don't actually need to even include any libraries, I'm pretty sure. Like it's just like in there. Size of, yeah.
no size of is part of the language.
Yeah, so like you don't include that at all, it's just like there. Ew, alright. That's disgusting. So like then like the executable that you create will then have that value like hard coded in there. So that's interesting. Alright, but anyways, just good things to be aware of. Oh, sorry. Good things to be aware of regarding Calec is the only difference that's really significant is the initialization, and then otherwise like there's not much. And the thing is, like in this class, like normally you'll end up doing your own initialization stuff anyways. So hopefully Malloc isn't really important for you guys. Or the difference between Malloc and Calec is really important. All right, so let's talk about failure. So what happens if Malloc? You know what? Let's talk about realloc and then we'll talk about failure. Just because realloc is kind of the nice thing to like go over. Realloc. There we go. There's an A in there. It's like real location. But that's not what it's supposed to be. It's reallocation because you're reallocating a section of memory. So at a high level, what does it do, do you guys think? Yeah.
So it probably like takes the memory space of whatever you put in, and then it clears it and reallocates it to whatever something else.
Okay, so that would be more of like, there is actually something that does that, that's memcopy. It takes in memory, definitely. But what it does, remember when I said early on, like what happens if we have like a classroom and we have like 100 students in it and then we realize we can get up it to 250? What are we needing to do there? What do we have to do to class? Like make it bigger, okay. Or like we could say making something bigger, we're kind of we're whatting it? Resizing it, yeah. So the idea is the reallocation is kind of like a resizing of a memory, a piece of memory. So the idea is you give it some memory, and like how do you like tell it a portion of memory? Like how do you like give that? Yeah. So yeah, you give it some memory of like your input. Really, this is like a pointer to memory. And then what do you think the other thing is going to be if we need to resize it? How many elements we want? Yeah. So we're going to basically say what's the size of the resulting memory piece we need. It's the resulting size, by the way, and a lot of people confuse that. A lot of people think it's the extra size. It's not the extra size. If you try to do realloc with -5, you're going to get funny things happening. So what you want to do is you want to give it the new size. So the memory of some input as a pointer, and then the other thing it takes in is the new size. New size. And of course, what do you think the new size is going to be in? What did we do for malloc? Number of bytes. Yeah, so the new size and the number of bytes. These are the arguments. So we're good there. All right, and what do you think it's going to return?
Pointer.
It's going to return a void pointer. All right. So the question is, well, if it's copying this memory over, like there's like kind of two situations we can be in, assuming that it succeeds. So I'll go over them. So imagine like I'm storing some piece of information. Imagine I'm storing something like ABC. Like you can think of like their like numbers or some values or something. Like this is something that's in my array. And what I'm doing is I'm going to go ahead and resize this. Now there's two things I can do. I can try making this larger, or I can try making this smaller. So let's go ahead and see what happens and make it larger first. So like if I try to make it larger, imagine like this is the old array, and what I need to do is I need to make it like maybe size 6. So there's going to be like some new values in here. New. It's going to be 6 in terms of its size. This was old and it was 3 size. So the question is, what do you think is going to be in this array? So any thoughts?
ABC and blank, not blank, but.
So you guys think ABC is going to be at the beginning? Uh-oh. Yeah, it is. All right, so it's still ABC. Sorry, I didn't want to make you nervous or anything like that, but just want to make you guys maybe think, well, could we have maybe put it somewhere else? It is ABC goes to the beginning, and then we have like some extra things here, and what are these guys? What do you think? Yeah, hands up. You have a question? Oh, what is it? Is it 0 bytes? Viewer thinks it's, well, there's like really only 2 options, right? So it's either going to be 0, so viewer thinks it's going to be 0. And what's the other option?
Undefined.
Yeah?
A whole bunch of undefined junk.
Random things or
Yeah.
something? Yeah, garbage? Okay, so viewer thinks it's going to be garbage. All right, more people think it's going to be garbage. It's garbage! Yeah, so we don't know actually what's going to be in these locations. All right. Okay, any questions on that? What's up?
So, reallocate will just turn the pointer back to a void pointer instead of like it was.
Yeah, so it takes in as argument really a void pointer. Do people cast it to void pointer when they pass it in?
No, because it's never an error to pass it any other pointer.
Oh, cool, that's awesome. So yeah, we don't even need to cast it. So I'll show you what it looks like in code. We'll actually do it both on paper, and then I'll do like a coding example so we can see it happening, right?
I just want to make sure.
Yeah.
you understand. So let's say old array was.
Like an
old
int star, right?
pointer is an integer. Would it go back to a void pointer?
It does go back to a void pointer. So you need to recast it. So like if you have some old array, maybe you created it, so you did old array, And again, I want to make sure that we see an example just so that way we're comfortable with this. So int star, and then we do calc 10 comma size of int. All right. So we're good with this so far? Like this is how we can create an array dynamically. So now let's go ahead and recreate this using real. Let's say that's like, oh, it actually needed to be 20. So what we do is we do old array, and this is going to make Jim cringe maybe a little bit. Star, and there's like maybe 2 reasons for cringing on this, potentially. So we're going to do realloc, and then we do old array, and then we do like 20 times size of int. All right, so there's like some problems with this, and that is like regarding how successes and failures work. So maybe this is a good time for me to go into successes and failures. But let's first do a coding example just so that we can actually see this working and not feel like uncomfortable about the material. Let's close that out. What is this? Reset. Oh look, here's some dynamic memory code. That's awesome. Nope, we're gonna use a different thing. S4. Alright, reset. So this is gonna be a reallocation example. So realloc example.c. Pound include standard, we need standard lib.h, and then we're gonna pound include standard io.h. What we're gonna do is we're gonna do int main. We're gonna do int star array is equal to, we'll do int star to pass it, calc, and we're gonna do 10 comma size of ints. All right, and then we're gonna fill it with some values. We're gonna say something like array of I is equal to I times I. So what value should be in the array at this point? Assuming everything works successfully. Like what's gonna be the first value of the array? Pop quiz. 0. Okay, what's gonna be the second value? 1. The next value? 4. 4.
It'll be
I squared, not I. Don't worry. I had someone that was like, why isn't it 2, 4, 6, 8? So that was a little bit rough. It was not a plus sign, it was a multiplication sign. All right, so what's gonna be the next value after 4? 9, not 6. What's the value after 9?
60.
16. All right, I think we know our squares. All right, so dumb question. All right, let's go ahead and now recreate this array. So array is equal to int star realloc array comma 20 times size of int. All right, so let's just print out to see what we end up getting. So we're gonna loop through all the values, I++, printf, %d, new line character, array at position I. All right, and assuming that everything works out fine, I should like free the memory at the end. Written, let's go into the other directory. All right, gcc realloc example, and then I can compile it, or run it. All right, there we go. And so it's running. Oh wow, that doesn't look like 100. That looks like a bit more than 100. All right, why is it not 100? What's wrong? Yeah? Okay, so yeah, exactly. When I was 10, we actually didn't do this call, and so we never actually filled the value with 100. So there was no 100 in the array. That's what's going on here. But then the question is, well, why is it this really crazy value here? It's the garbage. Yeah, it's the garbage that we got from doing realloc. So realloc does not do initialization, and this is just kind of demonstrating that. Yeah.
It's garbage, why are there zeros following?
Because we're lucky garbage. So that's what you want to hear. It's just probably because like it thought this value, it might not have thought this value, but it might have been like, oh, this is the value that we're going to copy over, and then like the rest of the stuff was maybe unreadable, and so it basically just filled it all with like 0 bytes or something like that. Like we might have, again, like we did get kind of lucky with this. But it doesn't have to be zeros. It could in theory be like really random stuff, but that's what it decided. All right, so there are some big problems with this because reallocation can fail, and that will cause issues. Also, calc can fail, that will also cause issues, and malloc will also fail, and that can cause issues depending on what you're doing. Does anyone know what return you get when one of these operations fails? I see someone with their hand up that I call them a lot, so I'm going to hopefully get any person. Yeah. No, very good. So if any of these functions turn, fail, so if any calc, malloc, or realloc fails, we get null. And there's like a little bit of an extra stuff that you need to be aware of. So the calc, malloc, and the calc and malloc are pretty simple, you just get null. But the realloc actually kind of opens up some kind of nasty cans of worms that we can end up getting here. So the big problem that realloc has when it fails is that sometimes people don't use realloc safely. What they end up doing is something like, really this. This is actually a kind of a problem when we're using realloc. And the reason why is because realloc, if it fails, it has an extra little caveat. So realloc, when fails, does not release memory, does not free the given memory address. So, all right, now why is that an issue? So, like the idea of these functions, by the way, calc, malloc, and realloc, they all kind of protect your memory. What they do is they prevent the rest of your computer getting access to this memory, and it also prevents like them like basically reading it and writing to it. You kind of like have a nice little safe section of memory that they kind of let you kind of roam around and sandbox in. And the thing is that the free really tells that your computer that I want you to have this memory back. You can go ahead and do with it what you will. But what that means though is that if you end up like kind of losing access to the sandbox, you kind of basically are kind of indefinitely protecting something that's going to like have issues potentially for you later down the line as you're running the program. I saw a hand up over here. Yeah.
Did you say does or does not?
It does not free.
You wrote that.
Oh, damn it. Does not free. Crap. Underline, bold, everything. All right. So thank you very much for pointing that out. Crap. Do what I say, not what I write. All right. Was there any other questions? Yeah.
Are there specific reasons that they'll fail, or is it just random?
Yeah, a pretty good way to get something to fail is pass in a negative size. So for those of you that don't know, calc, malloc, and realloc, they all allocate things in bytes, right? I already said that. Would you ever want to give like a negative size? Like would you ever want to allocate some negative amount of memory? Like that's basically saying to the computer, here, take my memory or something like that. You don't really have the authority to do that without telling what memory to take. So you can't really allocate a negative value. So the people that made C in all their geniusness, they said, let's go ahead and make it so that way all of the values that you're given are all the size T type. And size T is going to be unsigned. So what happens when you have an unsigned value is, what are the negatives? Does anyone know a little bit about negative numbers and their integer representation? Yeah. They're really big. So like -1 is actually the biggest number you can get. So imagine you have 0, all right? So you have a whole bunch of zeros, and then if you subtract 1 from 0, what's going to happen? Like if you have like 100,000, for instance, like so there's a lot of zeros in there, and you subtract 1 from it, what do you end up getting? You get, if you have 100,000, you get 99999 like a couple of times, right? So the thing is, really, how you can think of 0 is, and this is like maybe a bad way of thinking about it, is 0 is kind of like 1 with a lot of zeros in it. And the idea is this 1 is kind of hidden. So this is kind of like how binary works a little bit. I'm not going to go over too much the exact specifics of it right now, but we'll talk about this later. If you end up subtracting 1, so this is kind of 0. Kind of 0. So now if we subtract 1 from it to go ahead, because if you add 0 to -1, you should end up with -1. What you end up getting, if you like do some carry thing, is you get like a lot of 1s. In fact, what you end up getting is you get all the 1s. You get as many 1s as possible. So what you end up having is when you have -1 is the biggest number possible. And it kind of makes sense because if you add 1 to -1, you should end up getting 0. So the idea is like if you end up adding 1 to here, you get the overflow and it becomes a 0 value. But the problem that we end up getting here though is that if you now try to allocate something that's negative, you end up trying to allocate something because it treats it as a positive number. It's a really big value, and your program will end up saying, no, I'm not going to give you that much memory because I don't have enough memory in the computer to do so. So let's go ahead and see what happens if I try allocating with -1, because that's a lot of fun. So allocate with -1. We'll do that here at the beginning. And we'll skip this step because like it doesn't make sense really to do the copying if we're like creating -1 memory. Actually, if we don't skip it, then there might not be a problem. Oh, actually, does it? Yeah, it should give null. Actually, this is gonna work just fine because you can pass null into reality. Damn, this isn't gonna cause any problems. All right, let's cause issues because causing issues is fun. So what we're gonna do is we're gonna try to access the array after doing this initialization, just so that way I break things. Breaking things is good for us. Maybe compile. Okay. Let's see. Warning, argument 1. This is not exceeds the maximum object size, that is this value. So what it's saying here is, like, this is apparently what -1 becomes. That's a pretty big number. That, like, I guess if I add 1 to that, I'd end up getting 0. But so it's basically trying to create that much memory, and that's not, like, that's way too much memory. I'm not allowed to do that. So that is unfortunately not allowed, but like let's do it anyways. Don't laugh at me. All right, so now let's go ahead and run this and see what happens. Segmentation fault. Okay, and the reason why we're getting segmentation fault is this array here is actually a problem. So let's go ahead and see what array is equal to. We're going to print out %p with a new line character, and we're going to print out what the array pointer is. I think I did %p in class earlier, right? No? Okay. Well, %p basically allows me to print a pointer out, and since array is a pointer, I should be able to see what is stored inside that location. So I'm going to compile this. Yeah, I know that there's errors. Okay, cool. And segmentation's fault. Oh, because I didn't write. I'm an idiot. This is like the biggest problem that I have is, there we go. That's not null. But it is null. So NIL is basically the null pointer. So I'm trying to dereference null. That's a big violation. All right, but anyways, so back to what I was saying though, on paper. So because it doesn't read that memory, what's going to happen is if you have like some array, and you say this is equal to the realloc of the old array, and then like some value that's bad, what you end up doing is you create what's known as a memory leak. And the right, like, you can avoid this memory leak in a couple different ways, but the reason why this is creating a memory leak here is because if array ends up being the only copy to that section of memory, that only protected segment, and then I end up losing that information because I've overwritten it with the null value, now I can't go back to that protected section of memory and give that back to the computer. So this is a really big problem. It's why you should not do this, because we could overwrite protected address with garbage. It's kind of like you have an address to your house, and what you do is you go ahead and request that the post office gives you the address for a new house, but you give it like an invalid location or something like that. And what they end up doing is they go ahead and basically put on all your mail like some garbage like location. And the problem is you never have like a copy of your old house address for whatever reason. You didn't have that like stored in your brain. It's like it was just on that piece of paper. Now you're in trouble. Now you don't know where you live anymore, and that's like really unfortunate. They didn't like get rid of your old house, but they didn't like give you a new house either. So there's like some issues that we have here. So you shouldn't do this. If you want to be safer, you should always really check for null before you do modifications. So how you can do that is the following. So I'm going to show you how you do malloc safely to avoid dereferencing null. Because if you dereference null, you get a nice big old segmentation fault. So like pro tip, don't dereference null. If you want your program to work. But also pro tip, do dereference null if you want to find errors. So I know that's like really dumb sounding, but using a dereference and a null is not actually terrible in some situations. And I'll go over why that's the case in a moment. So doing this is going to cause a problem. So always check for null. Always check null when allocating. And with an asterisk here, homeworks don't apply. It's a good habit to get into, but I'm not going to require you to do null checks in the program, like your homework assignments. And if you have a situation where you're generating null in your homework assignment, you're already kind of in trouble, so don't worry about it too much. But it is a good thing to work on and to do. So let's go ahead and see how you can null check. Let's show a safe example of a malloc. So safe malloc, yay, you guys are super excited. So the safe malloc is to do the following. Int star array is equal to int star malloc, and then we do like 10 times size of int, which this should hopefully never fail. And then once we've done this, what we want to do is we want to check to make sure array isn't invalid. So we'll do something like, if array is equal to null, what does that mean? What happens if array is null? What happened in the malloc function?
There was an error.
There was an error, something bad happened. So what you want to do here is you want to handle your error. And the question becomes, what do you do to handle the error? And the answer is that's really up to you or to whoever you're writing this code for, because you can do a number of things. You could either return from the function, you could do some debug logging information and then like kind of skip some section of code. There's a lot of different stuff you could end up doing. Typically what I do in my programs when I have this sort of thing happen is I do some like print saying that we encountered this problem. I say where it occurred at, and then the idea is I can go back and trace it, and then I don't have to worry about like having something segmentation fault later or some garbage and like not understand what happened. So what's like a good idea to do is something like fprintf, and then use something like failed to allocate. Oh, cracker jacks. I need to do standard error first. Standard error, and then we do failed to allocate. So has anyone used fprintf before in class? Like not in my class, but in general? Hands? Like 2 people? Cool. Alright, you guys are asleep. That's fine. What does fprintf do? Yeah, in front. So it prints to a file. Okay, that's weird. Am I giving it a file location? std error. What's std error? Does anyone know? Has anyone seen that before? Don't worry if you haven't. So std error is basically the error output of your program. Your program actually prints the standard output, the standard error. If you have like some horrible thing happen, like you get like some error message that will come out. And most of the time when you use printf, that's like, well, all the time you're using printf, that's going into your standard output. So this allows you to go ahead and send something to the error channel instead. And the idea is like that allows people to kind of like if someone's like creating a debug log of things, they can go ahead and like print all the error that your program generates, as opposed to printing off like the output that you're getting. So it's just like kind of nice to do. This is my recommendation. You don't have to do this. Again, this is just like personal preference. And then of course like return like some error code. And you have to kind of define what that's going to be. All right, so there we go. This is how you safely malloc. How do you safely realloc? So what you do is ideally if you have like some like array that you're using, like we'll do an integer array. So you'll do instead like int new array is equal to realloc. Int star. I guess I can make that void star. Whatever. So int star realloc, and we can do old array, comma, and then you'll do like the new size, whatever that ends up being. So like new size is ideally the new size of bytes, so that's going to be your size of int times like however many things you're creating. And then what you do is you say, if the new array is null, then this is an error, only 2 L's, so you do your error handling. And then if it's not null, and of course, like you could probably return here as well, like whatever you want to fill, like wherever you want to return. And then like down here, if you didn't return, that means your new array was successfully allocated. So you do old array is equal to new array. And for what it's worth, there are 2 things that can happen when the when the memory is allocated successfully using realloc. The 2 things that can happen is one, it gives you the same section of memory, and if it gives you the same section of memory, it doesn't really have to do a copy, so it's like really fast and really nice. The other thing that can happen, which is a little bit more annoying, is it gives you a different section memory. And if it gives you a different section memory, it has to like do a copy to like move all the content from one location to another, and that can be slow. Order n is what's going to happen there, where n is like the number of elements. And you guys don't know about order analysis, so don't worry about that too much right now. I saw a hand over here. Yeah. Move things down. Oh, okay. Yeah, I zoomed in a little bit too much, so. All right, my apologies. Yeah. Yeah, so after you do the reality and you know everything is successful, then you can do old arrays equals new array. So it could be the case that if you're exiting your program completely at this point, you probably want to end up freeing your old array. So maybe free old array if you're like leaving your program entirely. Just so that way you don't create a memory leak. It depends on like what you're doing now. But so that's my recommendation. Does that answer your question? All right, any other questions? Yeah.
So when you do that, the old array equals new array, is all the stuff that was saved at the old array's location still there?
So it depends. So if the pointers are the same, then it's still there because it never moved. But if it did move, then it's undefined. We don't know if it's there or not. It could be left there, or it could be like overwritten by other things by this point. In which case, if you try accessing it, you could actually segmentation fault. So don't do that. Don't try to access the old array using the old pointer, because if the pointer is different, then doing so is undefined behavior, which is bad. Avoid undefined behavior. Like at this point, like so here, don't use old array, but here, you can use old array. Because the thing is, the address that old array is storing here might not be valid, but when you do this, what you're doing is you're updating the old array address to be whatever the address is for the new array, which is valid at this point and is usable. Yeah.
So this is the unsafe example for these?
No, this is the safe example. This is safe. The unsafe one was the one I showed at the beginning, where I said just array is equal to array comma size.
The one above?
It was here. This is unsafe. All right. So let's talk a little bit about memory violations and errors they can run into using this. By the way, dynamic memory makes a lot of problems for people when they begin using it, which is why students hate it so much. So the first thing that's like the easiest thing in my opinion to talk about, like it kind of like makes sense from what's going on, and it kind of introduces the next function, is the memory. So the memory leak is when you are not properly recycling your pointers by using the free function call. So the free function is what you use to give back your old piece of memory. So use free on any dynamically created piece of memory that you are done with. Failure to do so can cause issues, and I think that you kind of know maybe another issue you might have based off of what I just did. So what issue might you have if you change maybe one of these words? What word would change? Dynamically, what would it change to? Statically. So if you use free on static memory, bad stuff happens. Don't do that. So if you don't do this, what ends up happening is you keep protected memory that you don't get back to the computer, and after a limited amount of time, you'll end up crashing your program. So let's go ahead and see what happens when you end up doing that. So a very simple program we can do, vim no free .c. Oh boy, this is going to be messy. Pound include standard lib.h int main By the way, I should clarify, don't do this, please. All right, so what we're gonna do is we're gonna do a while loop, while 1, and what we're gonna do is we're gonna do int star pointer is equal to calc 1 comma size of int. All right. Anyone want to guess what I'm going to get as my output when I run this? So what do you normally get when your program stops working because you did something silly? Segmentation fault. Look, it's right there. Segmentation of forward dump. So we think we're going to get this, right? Let's see what happens. Standard I/O. I don't need standard I/O because I'm not printing anything in theory. I'm hoping. So GCC no freeze. Oh, you compiled. All right, let me reset, and I'll run it. Oh, why is it not stopping? What's going on here? Oh, it's gonna take a while. Yeah, it's a while. So yeah, that while one. All right. Anyways, so that's gonna take maybe a little bit of time. We're hoping for a segmentation fault. We'll see what ends up getting. So what would I do to? Oh. That's dangerous. Well, that never happened. So, please free your memory, or you can get that. That was not good. So, that was actually kind of exciting. All right, so reset. Free your memory. So let's go ahead and do the same program. But this time we're going to do it properly. So what we can do is we can use this function called a free function. So what the free function does is it takes in basically the address of the memory you were given when you created it dynamically. So how would I do that function call here? If I need to get the address, how would I do that? So I'll start it up. It's free, and then I need to give it the address. So what should I do here?
Pointer.
Pointer, just free pointer. This is all that you need to do. You just go ahead and say, this is the address I was given. This is the pointer I was given. This is the pointer. This is the address that you will take and free pointer. That's all that you need to do to go ahead and get this to, and I'm going to use air quotes here, but work. So what's GCC no free? And then we'll run it. And that's going to go for a while. And so I'm just going to let that cook, and we'll just go to another, back to this thing, and we'll talk about it. So, oh, I broke the projector now as well. Okay, no, we're good. So free takes the pointer created as input. And I really should say created dynamically. So if you end up doing something that's not dynamically created, it can very easily crash your program. So don't do that. So yeah, let's go ahead and talk about things that are a little bit more serious. So the big problem that we have with memory leaks is that older systems didn't actually used to be able to kind of handle what happens if a program terminates after taking a whole bunch of memory. Good news is modern computer systems are able to kind of recover from that. So that program I wrote didn't actually kill my computer, thankfully. But you can imagine on an older computer, I would probably have to do the rest of the class without the aid of the computer technically. So I really like modern computers. Allow me to go ahead and kind of run fast and break things. I think that's like a quote from some company, not sure. But yeah, it's good that you have these better computers, but it's also a little bit bad because it's kind of reinforcing bad habits with students where they don't try to be as safe as they really should be. But definitely be aware that if you do too many allocations, you can run into problems. You should be freeing your big point. All right. So let's talk about the next thing that is a big problem, dangling pointers. So a dangling pointer is just a really fancy word to say that you have a pointer that is pointing to a section of memory that is unknown if it could be used. So a pointer, a couple ways that you can have a dangling pointer is you recently freed. So the idea is if you're given something dynamically, imagine I do something like int star array is equal to blah, 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 blah. And then what I do is I allocate it using calc. And then I free it. Now what happens is after I freed it, I now have some piece of information, like some address inside this location, but that address is largely meaningless because that memory, that address is no longer protected. It doesn't actually destroy the variable, like an int star array. It just gets rid of the thing that array was pointing to. But that means that I really shouldn't be using that array and like overwrite array with new value. So like how that works is if I do something like int star array is equal to like, I'm gonna actually do the example that I just mentioned. Calc 1 comma size of int. And then I do free array. I do not use array at this point until you reallocate. So don't use array. Don't even free array, because that's kind of like using it. That's a bad thing as well. But then if I do something like array is equal to int star calc 1 comma size of int, now I can reuse it. So if you like reallocate that memory by doing another like calc call or like a realloc call if you like pass in some memory or you do malloc, then you'll end up like getting the ability to use this pointer again, no problem. Another way that you can end up getting a dangling pointer is by basically using uninitialized variables. It's a thing that I see a lot of students do, where uninitialized pointers. So the example is if you do something like int star array, you should not use array right now. If you begin using array at this point, before doing the calc call, you'll end up getting some problems. Like if you do something like array is equal to 0, or array of 0 is equal to 0, this is like segmentation fault worthy. So these are like the two ways that you can get dangling pointers. Now some people think, well, is it a dangling pointer if I do something like int star array equals null? The answer is, that's actually not a dangling pointer, because you know where it's pointing to right now. You know it's pointing to null. But a dangling pointer is really if you don't know where it's pointing to. You have no clue. And by the way, so I talked a lot about dangling pointers. I'll just switch over to my laptop for one moment. It's still running, so it didn't kill my terminal this time. Good news, that or my computer's frozen. Nope, we're still good. All right, so I'm going to stop it because there's no point in me continuing that, but I just figured I'd show you guys that it is able to go ahead and create and free the memory as many times as it wants. There's not an issue there as long as I'm getting that memory back. If I'm not using the free, then we have like some severe problems. All right, so these are like the two biggest times that you can get dangling pointers. Now you can also have a big violation, which is actually not a horrible violation, but dereferencing null. Does anyone know what happens if you dereference null? I kind of mentioned it earlier. So what do I mean when I say dereference null? How do you dereference something? How do you give a reference to something? How about that? Yeah? So yeah, so if you want to dereference it, you use the dereference operator. If you want to reference something, what is the reference operator? If I want to get a reference to something, what operator do I end up using? Yeah. The ampersand, very good. So if I want to dereference something, what do I use? I said dereference this time. So if I want to dereference, delta reference, yeah. Use the star, exactly. So what you should not do is do not do this. That's bad. Don't do this. That's also bad. What else should you not do? You shouldn't do something like this. And then this guy. That's the same as like that thing up there. Oh, I guess, does this work? Yeah, that's kind of fun. All right, don't do that either. That's weird. Oh, all right.
Well, actually, no, because you don't know the type.
Oh, really?
If you did.
Oh, okay, you're right. It has to be array, doesn't it?
If you did some
Ah.
ARR.
Yeah, then that would be a problem.
Failed.
That means these guys don't work as well then. Right?
Yes, because you don't know the type.
Yeah. So, all right. If you cast null, would that work then?
You what?
If I cast null? If I said it's an int star?
If you did star in star null, that would compile the crash.
Okay, that's disgusting. All right, but anyways, these are all going to cause segmentation faults. But segmentation faults is actually going to be kind of your best friend in terms of like what you could get as memory violations. There's actually much worse things you can get. So this is like the highest circle of hell. I'm not sure how hell works, but like this is like the least worst problem. Maybe I should just said the least problem. There we go. That makes sense. So this is like kind of an okay thing to get. If you end up getting a dereferencing null, if you get a segmentation fault, it's actually not the end of the world. Those are kind of easy to find. The real bastards you end up getting are like when you're using like uninitialized pointers. That's actually times where like the error could like happen, and then like maybe like a million instructions later or something the program crashes, and it's like, why did it crash in this location? And you have no clue. C is a really fun language, and if you're not careful, you can end up like looking in the wrong spot for an error, and that's happened to plenty of people. So just be very, very cautious of dynamic memory. It is an issue, and of course the biggest problem that people have are dangling pointers. Using them is a problem. Yeah.
So if we use Malloy, that'll still count as not initialized, or would it be initialized?
So the thing is, the pointer becomes initialized when you use Malloy. So even though the values in the address is not initialized, that pointer now becomes initialized. So it's really uninitialized pointers that we're worried about, not uninitialized data per se. I know that sounds similar, but it's a little different. This does require a cast, but you know, whatever. All right. So 4. Like using dangling pointers is like the big problem that we end up getting. So I'm just going to go ahead and like kind of summarize the thing that you'll commonly hear people say. So double free is another thing that you'll hear, but double free is really just using a dangling pointer. It's kind of like how squares are rectangles, but not all rectangles are squares. The idea is the double free is kind of a more specific problem that you have when using dangling pointers. And then, of course, similar to double free. So what do you think double free means? Let's go with that. If someone had to hazard a guess. Yeah? Yeah, so this happens when you free a variable twice. So you free array, and then free array. This thing here is called undefined behavior, and it's not fun. And your program can work, and the thing is, it can also decide to work, but then decide to give up after a little bit, or it can decide to just immediately crash. There's like a lot of different things can happen here, but there's no guarantee that you'll end up having your program work if you do this. So, how do we fix this? We fix this in a really fun way. The recommendation is, after you free a pointer, a really good habit to get into is setting that pointer equal to null. And you're wondering, why is it good to set a pointer equal to null? The good news is, like, if you end up dereferencing null, you end up having some problems, right? So if you end up using something after you freed it, if you begin using it after you free it, that's known as a use after free, which is another dangling pointer problem. So let me just write that down. Use after free. Another dangling pointer. And the idea is if you do something like free array, and then you do array of 0, this is also undefined behavior, don't do that. But the good news is if you go ahead and put something like, so like an anti-bugging technique, is every time you do free, so if you do free array, what you can do is you can say array is equal to null, and that actually fixes a lot of your issues. So as long as you kind of group these together, this actually fixes a lot of problems you would have. So why might this fix the problem? Can anyone tell me what would happen if I did like error 4 or 5 on here? So what does error 5 do? Like use after free. So let's say I tried using array after these 2 lines. So what's going to happen? What would that look like? Well, like how would I use array now after I freed it? Okay, so I could allocate it, but like if I wanted to use it without allocation. So the use after free would say something like array bracket 0, because I freed array, so I should not be using it. But the thing is, if I say array is equal to null, and then I say array bracket 0, what does the program do? It segfaults. And because it segfaults, like, so all of these I should, yeah, this is like the least problem, it does do a segfault. So it's going to segfault when this happens because we've done like array which is equal to some null value, and then we try dereferencing it. That's like that. So it will segfault. But the good news is it's better than using that value and not knowing what behavior you're going to get. Like, to go ahead and use some unallocated section of memory and then have your program crash like in a crazy time, that's really, really fast. So this is like a better thing to have happen because you can find out where this error is occurring at by looking to see what's the value of array at this point, like it's null. Okay, great, let's go ahead and do something now. Like you can use printfs and like this can help you out when you're having problems. So this is like really, really good. Like this is actually better than having the undefined behavior. Better than UB. All right. Then the next thing is we also fixed the double free. So what happens if we double free array? Like what would that look like in terms of code? So how would I do a double free at this point? Free array. So the idea is like, so assuming that like I was putting this up here, all I would need to do is say free array, right? So what happens if I free array? So what does freeing array do in this situation? What am I freeing at this point? Am I free, like, I'm freeing array, yes, but what is array, yeah? I'm freeing null, which is really weird. Does anyone know what happens if you free null? So, pro tip, or something that you guys should be aware of. Don't free static memory, it's undefined behavior. It's a bad idea. So the question is, well, is null static? No, not really. It's a special thing. So my question is, what happens if we free null? All right, so here are things that's going to cause a segmentation fault. Which is segmentation fault going to be good? Segmentation fault, anyone? No? All right. So here are things that's going to be undefined behavior, which is kind of a problem. Raise your hand. Like a couple people. All right. What? Like not many people raise their hand. What do you guys think it's going to do then? If not one of those two, yeah? Nothing. That's actually correct. It does nothing. Which is better than undefined behavior. And of course, this is like a really good thing to be aware of, and you should like do it in practice. One thing that I also want to mention before like we move on to like greener pastures is yeah. So I'll just write it down here. So don't free static memory. Memory not created by a dynamic memory function. So dynamic memory functions are things like callic, malloc, realloc, also sturduke, but we're not going to go over that. There's probably like more of them, but I don't really know because I don't really care. I don't even know any of the other ones. But it's just a good idea to not, like if you're doing something statically, don't free it. That's like a problem. So really like things like int array bracket 100, free array, bad. Is this undefined behavior? I think it is. If you free the static memory array, I'm pretty sure it's UV.
Yes, either you can't free static memory, you also can't free local variables.
Yeah, like, well, that's kind of weird. Like, if you free a local variable, like, if you try freeing x, or I guess you're trying to say ampersand x, right? Like the address of x?
You take the address of the local variable.
Yeah, so int x, and then free
Well, I mean,
ampersand. Oh, are you saying, like, just free x? Like, that's, like, gonna free, like, whatever value you have. Oh, okay, I see what you're saying.
that's not a static variable.
Yeah, it's still local. Alright, what's up? Yeah, so dangling pointer is, yep. Oh, it's screened up? Why is it turned off? Alright, there we go. So what I want to talk about is how do you create a string dynamically? So how do we create a string using one of these functions? Yeah? Yeah, so a string is really a character array. So what we're gonna do just real briefly, so that's the dangling pointers. So we are going to do a string. So string dynamic. So we do char star str is equal to, and then what? Like, let's say that I want to put Travis in here. So imagine I copied in my name into some string. Maybe it's a static. So I'll do char static. And that's like not good actually. So I'll do st. And then we'll do like, I don't know, 100. And then we can copy the contents of st. We'll copy Travis into st. So I have like a lot of things I wanted to do for this. Oh crap. Alright, so we'll do st comma Travis because I'm a narcissist. Alright, so we do that. And now what I want to do is I want to create Travis as a dynamic string. I don't want to go ahead and have this like st kind of lingering around. It uses a lot of memory. So if I can go ahead and turn str, like if I can turn it into dynamic memory, then like will be a lot better. So how do I do that? So we want to do malloc. So we do char star malloc. And then what do I put inside here? So the size of the char, I like that. How many am I going to create though?
7.
7? Why 7?
Well, because there's 6 letters in Travis, and then you want one for the end character.
Alright, but what if I read this from user input then? What do I do instead? What if it wasn't necessarily Travis? What if it was Alfred? Which, wait. Hey, no, shit. Alright, what if it was Alex? Ah, gotcha.
Oh, SCR length.
Yeah. We're going to do multiply by strlen of st, because st has the variable. Is that it? Plus 1. Yeah, all in one line. Ugh. Right. That definitely fits. But anyways, so this would be how we could go ahead and create a string dynamically, sort of. What did I forget to do? Yeah?
Can you zoom a bit?
I can. So I forgot to do one important thing here. Oh, free. Okay, fine. I'll do that. But what's in str? Nothing. So what do I need to do then? What am I missing? I need to initialize it. So how do I initialize it?
SCR equals.
Uh-oh. Yeah, I need to do a string copy. Don't do str equals. It's a big trap. That would actually compile, but what happens if I do str equals? Does anyone know? It changes the value of the pointer. So what happens then? You want to say something?
Oh, I was gonna say maybe it just outputs the number of the letter, like what that letter for.
So it won't like do the letter value, so you don't need to worry about that. But what happens is str is now going to point to st, but the problem is this memory that I just created using malloc, where's it going? It's going to go someplace different. I'm not going to be storing the pointer that was created dynamically. I'd be storing a static pointer, and by freeing it, I'd actually cause a vulnerability. If I did str equals st, what's going to happen here is this is going to become green static memory. And the reason why is because str now points to st. So this is like the wrong thing to do. The answer is no, don't do that. Instead we want to do strcpy, and we want to do strst, and that will make sure that we copy the contents and not the address. We want to make sure that we're not doing an address change, we want to make sure we do a value change. And this is how we would change the value. Alright, so this is how you can do a string dynamically. Let's talk about how we can do a 2D array dynamically. Yeah, we still need a free at the end of the program. Alright, let's talk about 2D arrays though. So 2D arrays. So how would I make a 2D array? What is it really a 2D array? Do you guys know? Like, how could you think of it a 2D array? I want to see if I can call them something different. Yeah. It's rows and columns. But like, so how do we have, like, let's not think of it as rows and columns. Let's just think of it as rows, I guess, for now. So if it's rows, what does that really mean? It's like, it's a 2D array is still an array of something, but what is an array? And it's an array of arrays. So how do we like write that out symbolically? How, like, what variable type do we end up doing if we're doing a dynamic array? Yeah. pointer. So we want to do a 2D array of integers. You would do something like int star star, and now that's like kind of allowing us to begin creating a 2D array. So let's go ahead and type that up real quick. So I'm going to call this grid because a grid is kind of like a 2D array, right? Maybe, ish. All right. And what we would do is we would say grid is equal to int pointer, and we do let's do calc, and let's say I wanted to make a Sudoku grid. Does anyone know how big a Sudoku grid is?
It's
9 by 9. So it's not a great example, but we can go ahead and do it dynamically. So what would be the first thing I want to put here? The size of what? Is it gonna be 81 because it's 9 by 9?
Size of 8.2?
Int pointer size? Is that what the first thing in calc is? Calc is like the number of items is the first argument. So how many items do I want to have? I want to have 9. And then what do I put for the size of each item? I didn't hear someone say it. Size of int star. Why is it int star? Is this storing an array of integers? No, it's storing an array of int pointers. So that's why we need to do that. And then the last thing we want to do is we want to do for int I is equal to 0, I is less than 9, I plus plus, and then we'll do grid of I is equal to, and so this only created kind of like an array of pointers to the sectors. If you want to think about this pictorially, what this did was it said, okay, this is grid here, and grid is pointing to a section of thoughts, a couple of them. But the thing is, all of these guys are supposed to be pointers, and they're all kind of dangling right now. And because they're dangling, that's not good. So what we're going to do is we're going to go ahead and make sure that they all point to something useful. So we're going to have each one of them point to their own row of values. And so how we do that is we say grid of I is equal to, and we do int star calc, other parentheses, I don't know how I did that, 9 comma size of what? Size of int now. So they're trying to create an int array at each one of these locations. And so this would be how you create a 2D array in C dynamically. All right, that's it. I will see you guys.